Alrighty, in this video here, we're going to be talking about 8.2, which is z-test for a mean. All right, so in our fifth objective here, we're going to test means when the population standard deviation is known using the z-test. So the statistical test called the z-test for a mean is used when the population standard deviation is known. When we do not know the population standard deviation, we cannot use the z-test and must use a different test, which is discussed in the next section. But we also have seen this in the last chapter when talking about the interval of confidence. So the formula for the test statistics is our test value will be the observed value minus the expected value divided by the standard error. So where the observed value is, the statistics, again, when the observed value is the statistic, such as a sample mean computed from the sample data, or the expected value would be the hypothesized population statistic. Such as the population mean that is expected if the null hypothesis was to be true. And the denominator of the is the standard error of the statistic being tested. Such as the standard error of the mean. Thus, the z-test is the statistical test for the mean of a population. It is appropriate when the sample is a random sample, either the sample is greater than or equal to 30 or the population is normally distributed. And the population standard deviation is known. So here's a better equation. So we can see we can find the z-score by taking whatever the sample mean is minus the population mean divided by the population standard deviation divided by how big our sample size is. Again, where the X bar means sample mean, mu is the hypothesized population mean, uh, lowercase sigma is the population standard deviation, and lowercase n is the sample size. So the first step for testing hypothesis is to check that the assumptions have been met. During this class, the assumptions are stated in the exercises, so it's always taken care of for you. So again, let's recall from the previous video the 5 steps of solving hypothesis testing problems. Again, remember step 1, we're going to state the null and alternative hypothesis and identify which one is our claim. Step 2, we're going to find the critical values. Step 3, we will compute the test statistics. And in step 4, we'll make a decision to either reject or do not reject the null hypothesis, and then step 5 is to summarize the results. So a sample statistics may be lower or higher than a hypothesis parameter without being significantly lower or higher. In other words, the difference may be due to chance. However, there is still a chance of a type 2 error or not rejecting a null hypothesis when it is false. When the difference is statistically significant, the null hypothesis is rejected, and the significant is the chance of making a type 1 error the researcher has set. So keep in mind that when a null hypothesis is rejected, there is a chance of making a type 1 error, and rejecting the null hypothesis that is true. Again, that last word there would be true. When a null hypothesis is not rejected, you may not accept it as true. There is just not enough evidence to say that it's false. When a null hypothesis is rejected, again, you may not say it is false. There's just, however, enough evidence to conclude that it is false. All right, so you never claim that something's true or false. You just say there is or is not enough evidence to say that it is or is not. All right, so now using the traditional method of hypothesis testing. So in example 4, we're going to talk about the z-test using the critical value method. On this one here, it says the average 1-year-old, both genders, is 29 inches tall. A random sample of 30 1-year-olds in a large daycare franchise resulted in the following sample of heights. Can it be concluded that the average height differs from 29 inches at a significant level of 0.05? Assume that the population standard deviation is 2.61 inches. So there's our 30 numbers. So let's kind of go through this. So let's get to the solution part so we have plenty of room to write. All right, so again, the null hypothesis is what the mean is equal to. So in this case, the null hypothesis states that the average height of 1-year-olds is 29 inches. So it is. And the alternative hypothesis states that the average height of 1-year-olds differ from 29 inches. So again, the null will always equal what the population mean is. And then the alternate is what we're checking. And we basically just simply say that it just differs. It doesn't say it's greater than, doesn't say it's less than. So this would be a not equals to 29. So in this case, again, they're asked, can it be concluded that the average height does differ? So in this case, the claim is the alternative hypothesis. We are trying to test that it does differ, like in some way that's not 29 inches with a significant level of 0.05. Remember, that's your alpha. However, this test is a two-tailed test, and the critical value here for the z-test will have to be alpha divided by 2. So that would be 0.05 divided by 2, which is 0.025. And then if you use the table E appendix A, you'll get negative 1.96. So that would be the z-score on the left. And then you will also use the positive version. So then z equals 1.96. Right, so you got both sides. So don't forget, if you're looking at it, you're like, well, I didn't get that for 0.05. Remember, you have to divide it by 2. All right, now we're going to use technology to find the test statistics. So we're going to enter the data and we're going to find the sample mean. And then we're going to use the 2.61 as the population standard deviation. All right, so let's do that real quick. All right, so in my calculator, let's go back to it. So again, you get another example of it. So again, I'm going to go to list and spreadsheets, and I'm going to type in all of the heights. So 25, 32, 35, 25, 30, 26.5, 26, 25.5, 29.5, 32, 30, 28.5, 30, 32, 28, 31.5, 29, 30, 34, 29.5, 29, 32, 27, 28, 27, 32, 29.5, 33, 28, 29. And that does give me 30, so I know I did it right. Or I didn't miss any. So I'll do menu, 4 for statistic, 1 for stat calculation, 1 for variable statistics. Number of lists, just 1. I want to take the list from A, but the results in B. And there we go. So the things that we need for our equation, where's our equation at? We need the population mean or sample mean. So we need this 29.45. And then we already have the population mean of 29. We're going to use 2.61 as our population standard deviation. And then we have our sample. So basically we have our mean. So let's switch back over. I wish I could get all that work back. Oh, well, I'll just go back from here. So again, we use technology and we determined that our our sample mean was 29.45. And then we have the rest of the stuff. So to answer the rest of it, we can now find the z-score. So the z-score would be 29.45 minus 29, which was the population mean, divided by the standard deviation of 2.61, divided by the square root of the sample space of 30. So I'm just going to simply type that into my calculator. That's going to be 29.45 minus 29 divided by 2.61. Divide that by the square root of 30. And I get 0.944349. All right, so and then we could probably just say that that's just going to be 0.9443, right? So there is our z-score there. So now it's time for us to compare the data. So this is what we got. And then remember where our critical values were to determine if I fall outside of it or not. So now to compare the critical values in the direction to test statistics, in order to make a decision, we're going to choose the appropriate decision. So again, we got a z-score of 0.9443, and our happy range, or our critical range, was between negative 1.96. Hold on. What did I write down? Yep, 0.96. So between negative 1.96 and 1.96. I can see that this falls in between it. So therefore, I do not have enough evidence to reject my null hypothesis. So I'm going to select do not reject the null hypothesis. And again, it's because this fails. So again, remember the graph looks like this. This is my good region. This is where I do not reject my null. This is outside of that. So if this number would have been less or greater than this, then I would have rejected the null. But in this situation, there is not enough evidence. 0.45 is not enough evidence to reject the null hypothesis. Now, there is, again, not enough evidence to support the claim. Remember, our claim was our alternate hypothesis that the average number of 1-year-olds differ from 29 inches. And again, because we could not reject the null, then we cannot accept the alternative hypothesis. So we just simply say there's just not enough evidence to support the claim that there is a difference in 29 inches. All right. So that is how you do a test right there. So now you got the formula, you got the whole process. Now, remember when the test statistics falls in the critical region, your decision is to reject the null hypothesis. Again, we were in the non-critical regions where ours fell. It indicates that the difference is not likely to have been due to chance. Right? So if I would have fell outside of the positive or negative 1.96, then I would have fell in the critical region and we could then have rejected the null. Also remember, when the test statistics falls in the non-critical region, the decision is to not reject the null hypothesis, and it indicates that the difference is likely due to chance. All right. So we're saying that 0.45 just happens to be the babies that you chose, and really it is probably 29 inches. All right. Now we're going to talk about how to use the p-value method for hypothesis testing. All right, so using p-value methods for hypothesis testing, usual levels of significance used to test hypothesis, again, remember, are 0.05, 0.01, and sometimes 0.10. Right? Very rarely do they want 10% of a probability of being wrong. The choice, again, depends on how important it is that we do not make a type 1 error. So again, we're going to use technology has made finding another statistic, the p-value, for the hypothesis test. So p-value is a probability level of getting a sample statistics, such as the sample mean, or a more extreme sample statistics in the direction of the alternative hypothesis when the null hypothesis ends up being true. So let me get this part up. So in other words, the p-value is the actual area under the standard normal distribution curve or other curves, depending on what the statistical test is used for, representing the probability of a particular sample statistics or a more extreme sample statistics occurring if the null hypothesis is true. All right, let's look at our first example here, or example 5, but the first one for the day. Decisions for a p-value for a different significant levels. So suppose a computer printout shows a p-value of 0.0356. What do we do with that? Well, let's look. All right, so for an alternate hypothesis, we're stating that the mean is greater than 50. This is just a random thing. And the sample mean ended up being 52. I don't know what's going on here, but this would be at a alpha of 0.05, meaning that with a 5% probability there, the null hypothesis will be rejected since the p-value is less than alpha. So since we got a p-value from the previous statement of 0.0356, since this guy ended up being less than 0.05, then we can reject the null hypothesis, because it's basically what's happening is we're good with a 5% probability. Our probability value basically just came out and said, well, really, you have a 3.56% chance of you being wrong. So now we're like, all right, we like those odds. We're going to reject the null hypothesis. All right, so that's another way to look at it. However, if the same hypothesis test was used, and this time we wanted a 1% probability of getting a type 1 error, Now the null hypothesis is not rejected because the p-value is greater. So again, we got a 1% what we want to be. This showed us that there's 3.5%, 3.56% chance of you being wrong. And so that's too much of a risk if we want only 1%. So therefore we'll say, you know what? There's just not enough evidence to reject the null hypothesis. So we won't reject it. So just really depends on how large of a probability you want to make. So if the hypothesis test is a two-tailed, the area in a one-tail must be doubled. For a two-tailed test with a 0.05, the p-value of 0.0356, and the p-value for two tails will then be 2 times that, which is 0.712. Thus, the null hypothesis will not be rejected for a p-value that is greater than alpha. So basically what it's stating, if you have a two-tailed test for a certain alpha, you have to times it by 2 for the p-value. And then if that number is less than your alpha, then you can reject. In this case, when we doubled 3.56, we got 7.12, and therefore that is now larger than our 5%. So therefore, we're going to say, you know what? We're just not going to reject the null hypothesis on this two-tailed test. There's just not enough evidence. All right. Decision rule when using a p-value. So again, if the p-value is less than or equal to the alpha, we reject the null hypothesis. So if it's less than our probability of making a type 1 error, then we can confidently reject the null hypothesis and then say that there's enough evidence to support the alternative hypothesis. If the p-value happens to be greater than our probability of being wrong, then we're just simply just going to not reject the null hypothesis. There's just not enough significant evidence to go against the null hypothesis. But again, notice that the alpha is chosen by the researcher, not us, before the statistical test is conducted, while the p-value is computed after the sample mean or the test statistics has been found. So again, the alpha chosen before we even start, and the p-value computed once we have all information, and that's another way we can compare things. So for a z-test, you can use table E and appendix A to find the p-values, or use technology to find the, you can use table E and appendix A to find your p-values as well. Or we can use technology, but we've been using the table, so that's what we'll stick with. First, find the area under the standard normal distribution curve corresponding to the z-test value. So for a left tail test, use the area given in the table. And then for a right tail test, use 1 minus the area given in the table to find the probability value. For a two-tailed test, double the area you found in a one-tailed. However, calculation computer softwares that calculate p-values calculate the actual p-values. So subtracting and doubling are not needed. We're again using table E, so we will be needing that. All right, so here's the procedures of solving testing problems using the p-value method. So state the null hypothesis, null and alternative hypothesis, and then identify the claim. That's always the first thing. Then step 2, you're going to compute the test statistic. Step 3, find the p-value, so the probability of the area under the curve corresponding to your z-score. Step 4, make the decision to either reject or do not reject the null hypothesis, and then summarize the results of your findings. All right, guidelines for p-values. So again, the p-value is less than or equal to 0.01, we reject the null hypothesis. The difference is highly significant. Okay, so just flat out, regardless of what alpha is, if it's less than 0.01, you're rejecting it. If the p-value is greater than 0.01, but p-value is less than 0.05, then we could reject the null hypothesis, and the difference is just significant, again, depending on what you're looking for. If you're looking for something 5% or less, then we can reject it, but it's not highly significant, it's just significant. If the p-value falls between 0.05 and 0.10, we'll consider the consequences of a type 1 error before rejecting it. So really just depending on how close we are, we really need to debate, are we okay with being under 10, or do we want it to be under 5%? And then we have to debate if we're going to reject it. And then flat out, anytime the p-value is greater than 0.1, we're not going to reject null hypothesis at all. It's just too big of a chance of that we could be wrong. Remember, the p-value is telling us the probability that we're probably going to be wrong. So if it's greater than 10%, we're not going to take that chance, and we'll just say the difference is not significant. All right, so with that, let's look at an example. So we'll look at example 6 here, talking about soft drinks consumptions. So a researcher claims that the yearly consumption of soft drinks per person is more than 52 gallons. In a sample of 50 randomly selected people, the mean of the yearly consumption was 53.7 gallons. The population standard deviation is 3.5 gallons. And then find the p-value for the test. You may use technology or the table. Again, we'll be using the table on the basis of the p-value. Is the researcher's claim valid? So again, we need to state the null hypothesis. Remember, the null hypothesis is that it's going to be equal. So in this case, that would mean that the average of the yearly consumption of soft drinks per person is 52 gallons, right? So that is your null hypothesis. And again, that looks like this right here. We're saying that the population is going to be equal to 52. Now, the alternative hypothesis is just basically stating that the average daily consumption of soft drinks per person is more than 52, because we saw that it was 53.7. So now our claim is that the average yearly consumption of soft drinks per person is more than 52 gallons. And this is again, well, sorry, and then that would be, you would see that the alternate hypothesis would be that we are greater than 52. And so you will see that this is a right-tailed test because we're looking at the stuff to the right of it. And then we got the null hypothesis, we got our alternative hypothesis, and then notice the alternative hypothesis is my claim. I'm claiming on the basis of the p-value, is the researcher's claim valid? So the researcher claims that yearly consumption of soft drink is more than. That is what my claim is, right? So I got to see is if he's correct or not. So now the z-test for the so the test statistics for the z-test is the mean, which they did for us. We got 53.7 minus the population mean, which is 52, divided by the population standard deviation of 3.5, divided by 50 randomly selected people. So that'd be the square root of 50. So I'm going to type that into my calculator real quick. And I see that I get 3.43452. All right, and I'll just kind of round that to about 3.43. Now, to calculate the p-value, let me kind of show you that. I wish we had the table on this one. I got a T table coming up. Hmm. Um, let's see. Give me a second. I want to pull up your table so you can see it. This takes time to download the book. All right, I need appendix A, table E. All right, so I'm going to share this with you real quick. All this math is going to disappear, so make sure you have it. We're looking for the probability value, so I need to go to the z-score 3.43. All right, so here we go. So I'm looking for the z-score of 3.43. There's 3.4. How's it go? 0 first. Okay. So 3.4, 0, 1, 2, 3. So I see that the probability there is 0.9997. All right. So when I come back, I take that again, that z-score, and I got the 3.43, and I got the p-value then was 0.9997. Now I realize that this right here is a right-tailed test. So I'm looking for anything that's greater than. So the 0.997 is actually the area under this entire curve. So to get the correct one, I need to do 1 minus 0.997, which gives me 0.0003. All right. And then I'm not focused on the technology part, but there's our probability then. Our p-value ended up being 0.003. So you still do the z-test, and then you go over here and you just determine what it is. So what happens is with the p-test is you don't have to go find critical values. I don't have to go to determine what is my critical value so I can determine my range or whatever it is that I need to determine. All right, now that I got my p-value, again, which ended up being 0.0003, because it's less than 0.01, I can instantly, regardless of what the critical conditions I want, the decision is to reject the null hypothesis. Hands down, with a pretty much with a 0.03% probability of being wrong, I'm confident that I can reject the null hypothesis here. And again, with highly significant difference. Now, the part 5 here is so basically, we're going to write this out. So there is sufficient evidence to support the researcher's claim, because that's what, if we're rejecting the null, then we're supporting the alternative hypothesis, which ended up being the researcher's claim. So we'll support the researcher's claim that the yearly consumption of soft drinks per person is more than 52 gallons. And therefore, the test supports the decision that the researcher's claim is valid. Right? So again, we did not even need a critical value because our p-value was so small. If it would have been larger than 0.01, now we got to determine, if it's between 0.01 and 0.05, what is our confidence level? If it's less than 0.05, we can take it. And then same concept. If it ends up being between 0.05 and zero point 0.1, is our probability okay at 10% or less? If it is, then we'll reject it. If it's not, we fail to reject. And then, of course, then anything greater than 0.1, we instantly fail to reject. This is too high of a chance. All right, and that's pretty much going to be the conclusion of this video. We'll look at t-test when the population standard deviation is not known. If you have questions, again, always reach out. As always, I'll see you in the next video.